Alright guys, we're going to start Vodcast 3.1. This is the most important single thing in all of chemistry is learning moles. If you don't get this, then everything else is pretty tough. So we're going to do a short little video clip to talk about what it is, and then we'll get into notes.
Okay, I want to give you a quick idea of why we would use something like moles. Like, this is a relatively small amount of little styrofoam pieces. These are like the little packing things that we use to pack stuff up in boxes and ship them everywhere. And on the table here, I mean, I've got, I don't know, 50 or more of those. I don't really know exactly how many there are. I could count them all, but there's quite a few. And so the way that moles work to make this a little bit easier is that basically if I know how much one of them weighs, then I could weigh them all, and that would basically count them by weighing them. So to do that, come over to a balance. Okay, we're going to zero the balance out. Okay, I've got my little weigh boat on there. I'm going to put, let's see, 1, 2, 3, let's try to make sure they're the same size, because otherwise this doesn't work real well. I've got 4 packing peanuts on there, and so 4 packing peanuts is 0.5 grams. Okay, now, so if I take all of those packing peanuts, so hang on. Oh, whoops. Got to tear the beaker first. Okay, so we zeroed it out, so we're not taking into account the weight of the beaker. And let's just say I grab a ton of these peanuts. Okay, chuck them all in there. Okay, and so if 4 packing peanuts weighed 0.5 grams, that basically means that they each weigh 0.125 grams. And so now I've got them all in a beaker, and I've weighed a whole bunch of them, and it says 18.7 grams. And so then I could just use that as a quick little conversion factor and be able to figure out how many packing peanuts I had. And I'll try to pop that up in a pop-up for you. But it's 18.7 grams, and they're basically 4 of them weigh 0.5 grams. And so now I know how many there are just from doing that without having to count. I could do that with a big giant bag or just this little tiny bag that we have right now.
Okay, so the essential point behind using moles then is that moles are counting by weighing. Okay, and why this is really useful to us in chemistry is that the things that we are trying to count in chemistry, atoms or moles or ions or things like that, are so incredibly small that we need an easier way to do that. Okay, and so that's what a mole is. And what a mole is then is a mole is going to be 6.022 times 10 to the 23rd particles of a substance. Now what does that mean? That means it's basically the same thing as a dozen. Okay? You can think about it like the same way that you would a dozen. Like a dozen eggs is 12 eggs, a dozen donuts is 12 donuts, a dozen students is 12 students. So a mole of atoms is Avogadro's number of atoms. It could be of bananas or pieces of sand or anything like that as well. Would work equally well there. So we're going to use this all the time, and these are the 3 ways that we typically are going to use it. Is that a mole is going to be equal to that many atoms, a mole is going to be equal to 6.022 times 10 to the 23rd molecules, or formula units. Okay, so into the calculations. This is where it gets a little bit more complicated. So this is our essential conversion factor. 1 mole equals Avogadro's number of atoms, and our example here says how many moles of magnesium is 1.025 times 10 to the 23rd atoms of magnesium. Okay, so our given is that number, okay, 1.25 times 10 to the 23rd atoms, and our unknown is moles. So we set up our railroad tracks for our conversions. Okay, we're going to put our given in the upper left box. That's, kind of always our rule there, so that's what we start with. And then following our rules of conversion factors, what I want to go down in the bottom box is atoms. Okay, I need atoms to cancel out, so I'm going to put Avogadro's number worth of atoms down there. Okay, so 6.022 times 10 to the 23rd, and that's atoms. And then on the top of that goes the other half of the conversion, which would be moles. Okay, now in our calculator, the way that that's going to work is we're going to punch in 1.25 times 10 to the 23rd on top, and divide it by 6.022 times 10 to the 23rd on the bottom. That's going to give us 0.208 moles when we round to 3 sig figs, because our given has 3 sig figs. Okay, and this example basically is just to show you that you really have to be cautious with what the problem asked when you're doing mole conversions. You can't just do what some of you all do and just say, I'm just going to multiply stuff, or I'm just going to divide stuff. If you look at this, it says how many atoms are in 2.12 moles of propane. Okay, so if it's propane and it's a compound, then what Avogadro's number means is that 1 mole of it equals that many molecules. Okay, the problem is the question asked for atoms. So what we additionally know is that there are 11 atoms in 1 molecule of propane. Ooh, sorry, quick sneeze. So what that means is that in this problem, we're going to need 2 conversion factors. We're going to start with our given. Our given is 2.12 moles of propane. And it's real important that at this point you start writing down what it is. Okay, you can either write, like in this case I wrote propane, or you can write down the formula. But you really need to start labeling these things, because pretty soon we're going to be into stoichiometry, and what it is going to change in the middle of the problem as we do a chemical reaction. So our unknown's atoms. Start with your given, upper left-hand box of your railroad tracks, always the way it works. Again, we're going to label that with the formula. And then, so what do I want first? I want to cancel out moles. So I'm going to use my 6.022 times 10 to the 23rd molecules equals 1 mole. 1 mole goes on the bottom, so that'll cancel first. Molecules goes on the top. Okay, so when I cancel out moles, I'm going to be left with molecules. Now, molecules isn't what I want for my final answer. That's not my unknown, so I need 1 more conversion factor, and that's this 1 molecule equals 11 atoms thing over here. So I put 1 molecule on the bottom, 11 atoms on the top, cancel moles, cancel molecules, and so then what I'm going to be left with once I punch this in the calculator is 1.40 times 10 to the 25th. Okay, atoms. This is also why it's real important that you have to make sure that you put the exponents on there, that you can't just leave that stuff off. Okay, you can't just put in 1.40, that's way off. Okay, you got to put everything in there. So, on your sheet, on your note sheet, on number 3, and I know that it's weird that we start with number 3, but you'll see why here in a minute. This is how we convert atoms to moles or moles to atoms. So number 3 says how many moles are in 2.997 times 10 to the 25th atoms of vanadium. So write down your given. Okay. Good news is at this point you got one number pretty much, and that's probably your given. So we got that as our given. Our unknown then is moles, and we need 1 easy conversion factor. Okay. Avogadro's number of atoms, 6.022 times 10 to the 23rd, equals 1 mole. Okay, so that's our conversion factor. Relatively simple. Wow, sorry for that giant sniffle, guys. Okay, so now we set up our railroad tracks. You put your given, top left corner, always, 2.997 times 10 to the 25th atoms. Okay, I want atoms to cancel out. Alright, so that is what is going to go on the bottom for my first conversion factor. So 6.022 times 10 to the 23rd atoms. Okay, that cancels. And then on the top goes 1 mole. That's the other half of the conversion factor. Okay, now I didn't really write down what it is in this case. It's vanadium, V. I probably should have. Okay, so you should just get in the practice of writing those. So again, this is where we're going to divide 2.997 times 10 to the 25th divided by 6.022 times 10 to the 23rd. We're going to get 49.77 moles. Okay, we cancel atoms, 4 sig figs in my given, so that gives me my answer of 49.77. Okay, relatively straightforward. Make sure you got this down in your examples. Number 4, basically we're working the other direction. Okay, we're given moles, and we're asked to find atoms. So our given is 0.000034 moles of helium. That's 5 zeros if you're trying to copy that down after the decimal. Remember, that's only 2 sig figs because those are all leading zeros. They don't count. Our unknown is number of atoms. Okay, and so we've got our same conversion factor. Our conversion factor is still 1 mole equals 6.022 times 10 to the 23rd atoms. Okay, it's atoms because we're not talking about compounds yet. We'll get to those probably in tomorrow's vodcast. Okay, so pretty straightforward. Grab that, start our railroad tracks, put our given in, make sure you get all those zeros correctly. Okay, so I've got that many moles, and I should have put helium, but I didn't. Okay, should label it with what it is. And on the bottom, we want to cancel out moles this time, so moles goes on the bottom. On the top goes Avogadro's number. And this is where it's real important to know how to do conversion factors, because if I divided that, I would have gotten a vastly wrong answer. If in the previous one I would have multiplied, I wouldn't have got anywhere near where I needed. Okay, so in this case, they're both in the numerator on the top, so we're going to multiply them. So when we multiply them out, we're going to get 2.0 times 10 to the 18th. Real important that you keep those exponents. Okay, that's how many atoms we have. Cancel out moles, and that's what I'm left with is atoms. So pretty straightforward. We'll work some practice problems, and then we'll make them a little bit more complicated in the next vodcast. Not really, but we're going to add in the real use of this in the next one, which is what grams, because that's what we actually want to do. We said moles are counting by weighing, and so that's what we're going to get to in the next step. Thanks, guys.